We are recording today's presentation. We will turn it off during the question and answer session so that you can feel free to speak freely. We'll just be posting the recording of the presentation on COBRA's YouTube channel. If throughout the presentation you have questions, please feel free to put them in the chat in Zoom. We'll save questions for the end, and you can either ask them, you can raise your hand to ask the questions, or I can read the questions that are put in the chat. And here we go. So without further ado, it is really a great pleasure to welcome Dr. John Jamieson as our speaker today. He's joining us from the University of Ottawa in Canada, and he'll be speaking with us about marine minerals and economic geology. So thank you so much, John. I really look forward to your presentation today. And you are on mute.
All right, check 1, 2.
Yep, we can hear you.
All right. Now, I practiced sharing my screen several times so as to not screw this up. Okay, great. Thank you for the invitation to speak at a COBRA seminar. I've attended many of these, and so it's a privilege to be on the other side for a change. My background is economic geology, which is the study of mineral deposits, how they form, how we find them. I've been doing this for just over 20 years, and then I've been working on the seafloor since about 2008. And before that, my background was land-based mineral exploration. So this topic is assessing the resource potential of seafloor massive sulfide deposits. I'll start off by saying resource potential is not an assessment necessarily of whether we can or should mine. It is a purely geological concept, and we'll talk about how you go from resource definition to whether or not we can or should mine. But I think it's important to start by saying that when we talk about resource potential, it's a purely geological approach. So the relevance of all of this to the COBRA community is that with the idea that we could potentially mine seafloor massive sulfide deposits, they of course host ecosystems, which many of you study. So a resource assessment, and I'll be talking about this in terms of a few individual deposits and at a global scale. It is kind of an assessment of the risk of seafloor mining to these ecosystems. So we start with seafloor massive sulfide deposits. So these form due to the action of hydrothermal fluid circulation through oceanic crust, and hot fluids heat up. They leach metals from the crust and transport them to the surface, mix with seawater, and you dump out minerals at the seafloor, and some of the minerals get ejected into the water column. That's the smoke. And you form these, what we call massive sulfide deposits, accumulations on the seafloor. This is one example. This, let me get out my nifty little pointer here. Pointer options. Right, so this is an example based on sort of the tag model, which is sort of commonly used. Very few massive sulfide deposits on the seafloor actually look like tag. So we really need to diversify our examples, but it's very illustrative. You have chimneys that are forming on the mound. An important thing to note that a massive sulfide deposit, when we think about it from a mining perspective, It's the mound. That's where most of the material is. The chimneys are these little sort of bonus things on top. It's the icing on the cake, but it's the mounds themselves that make up the deposits and the value. Massive sulfide, the term massive has nothing to do with size. It's a textural term. A sample that is massive in terms of, in this case, sulfide, so sulfide minerals, pyrite, sphalerite, chalcopyrite. It's a sample that basically contains the majority sulfide minerals. What that number is, people debate, but usually around 60, 70% of your formation is made up of sulfide minerals. That's what massive means. So you could have a small massive sulfide deposit or a big massive sulfide deposit. And they are rich in copper, zinc, gold, and silver. Those are the primary metals of economic interest. Okay, so I'm going to start by discussing how we find an ore deposit, a mine on land, and then relate that to how we do it in the ocean. So on land, you start with a old-timey prospector. You have to have a hat, a gun, usually a big mustache, beard, and a donkey with some pans and shovels. If you don't have a donkey with pans and shovels, you're never going to find anything. So prospecting is you have geological knowledge, you have geological maps, you have a geological degree, you know something about mineral systems, and you go out to areas where you think it is prospective for whatever metal you're looking for, gold, silver, copper, uranium, lithium, diamonds, doesn't matter. And it's low tech. Well, it used to be low tech, but it's cheap and there's a lot of wandering around. In the modern world, we still have geologists who basically go around. We don't use donkeys as much anymore. But you have maps and you go around smashing rocks and looking for signs of mineralization. It's become more high tech. We now use things like airborne geophysics. This is a helicopter doing an electromagnetic survey over top of a volcano. So what we're doing here is we are prospecting. We're looking for any signs of mineralization, any signs of the valuable metals that we are interested in. And we've been doing this on the seafloor for decades. So here's a map with all the data from the Interridge database. So I just took all of that. There's over 750 dots on this map, and they are split up into active hydrothermal systems on the seafloor, active but unconfirmed. These are plumes, but we've never traced the source of the plumes. And then there are the green inactive sites. Last month's COBRA talk by Jason Sullivan and Amanda Ockberger, very nice description of inactive sulfide deposits. So we've been prospecting on the seafloor. In our case, this is plume hunting. This is mainly how all of these sites have been located. And as a community, as you can see, we are actually very good at it. We know where to look. We have the geological information, and we go and then we find signs of mineralization. Okay, what happens next? If we go back to land, you find something, you're out in the wilderness, and you find let's say you're looking for gold, you find a quartz vein that has some gold in it. And you're like, oh, okay, there's some prospectivity here. There's some indicators that we have a gold system. And so you start spending money. You bring some people in, you might set up a temporary camp like we have here, and you start delineating that deposit. You have a quartz vein. How thick is that vein? What is the extent of that vein? How much gold is in that vein? What you're trying to understand is the geometry the size, the extent, and the composition of your deposit. And this whole time, you're trying to understand two things. Is it big enough and is it rich enough that it could one day be a mine? So is it big and is it rich? The term we use in economic geology is the grade and the tonnage. What is the grade? What is the tonnage? It has to be big enough and it has to be rich enough. So at this stage, you're trying to understand that. So you do a bunch of work. You might spend a few $1,000,000 over a summer. You might come back several years. On the seafloor, we do the same thing. We find a plume. Well, okay, where's that plume coming from? What's on the seafloor? We might use an AUV. We could put all sorts of sensors on it to map in high resolution, or geophysical sensors, environmental sensors. Here's an example of a magnetic susceptibility map that was created with a magnetometer on an AUV over the Solwara 1 deposit off the coast of Papua New Guinea. The magnetic data in this case gives us some information on upflow zones, high temperature hydrothermal upflow zones. Also from the Solwara 1 deposit, this is a map from Nautilus Minerals from one of their technical reports. And the red areas you see are this is an electromagnetic survey. Massive sulfides are generally more conductive than the surrounding rock. And so Nautilus Minerals ran one of these surveys and they were able to very nicely delineate the extent of their sulfide deposits on the sea floor. Again, in all of these cases, trying to understand the size, mostly in this case, not so much grade right now. If you want to understand grade, you need to go down to the seafloor and actually sample. So again, in this case, we'd be using an ROV, most commonly how we do that. I suppose you can dredge or use manned submersibles, or anyway, there's lots of ways you could pick up a rock from the seafloor. But that information is required to understand the concentration of the metals in your deposit. And if you keep getting positive signs, it's looking like your deposit is quite big and quite rich, you're encouraged. You're going to spend more time and more money developing that deposit even further. You're going to come back over several years. You might set up an even bigger, somewhat more permanent camp. Here we have some roads, some buildings. So this is a serious project. And you get to the point where one of the most valuable things you do is drill. And what you do when you drill is you are trying to ground truth all the other exploration you've been doing up to that point. Geophysics, mapping, modeling, that all gives you an indication of what might be underground, but it is drilling that really gives you a reliable answer. What you are doing is you're extracting rock cores from the subsurface. So here's a drill core logging tent, and the geologists are going through all of the drill core there, stacks of it here. And this is expensive. You only drill when you think you really are sitting on top of a deposit that has high enough grade and high enough tonnage that it could possibly be a mine one day. Now, the seafloor, drilling the seafloor is very difficult and extremely expensive. It's been rarely done. Again, I'm going to go back to the example from Nautilus Minerals. They're essentially the pioneer in drilling to delineate an ore deposit. They're essentially the first to ever attempt to do this on the seafloor. There's been other drilling with IODP, for example. But if you look at this map here, so the black outline is that same extent of the electromagnetic survey. And all of these dots here are where they drilled into the Solwara 1 deposit. Over 250 holes. They recovered about 2,800 meters of core from this deposit. So that averages about 10 meters per hole. This is done using a drill mounted on a ship, in this case, the DP Hunter, and they also used a drill that they lowered to the seafloor and was essentially controlled with an ROV. And they did four campaigns starting in 2006 and the last one in 2011. And they used this information to define the size and the grade of their deposit. All that core is sitting in a container in Brisbane, Australia. Here's the container. These are all core boxes in there. This is what $80 million of seafloor drilling looks like, all stacked into that one container. Here's a photograph of that core. It's starting to degrade because of the exposure of sulfide minerals to the atmosphere. Okay, so what Solwara did, what Nautilus Minerals did, is they took all this information and they defined, the first time ever on the seafloor, a resource assessment of the Solwara 1 deposit. So if we look at this table, this is from their technical report. So there's Solwara 1, there's Solwara 1 North, which is just sort of a step out from the main deposit. They have different classes. I'm going to come back to what these words mean. And they split up their deposit into chimneys, sediment, sulfide dominant is essentially the mound. It's the massive sulfide that makes up most of the deposit. And they have tonnages and they have grades. And these are estimates, interpolations based on the analysis of the drill core that they collected. Okay, and in the end, they ended up with, in total, just over 2 million tons at around 4% copper. And we'll come back to those numbers and what they mean. All of this, you can download this entire report off the internet. And here's what the front page looks like. The most important thing on this front page is this little sentence right here. Technical report compiled under NI 43-101. National Instruments 43101. So Nautilus Minerals at the time was a publicly traded company listed on the Toronto Stock Exchange. And the Toronto Stock Exchange has essentially a rule book for how mining companies report the results of exploration. So every company has to sort of follow this template so that you don't swindle the investor with a bunch of bunk. So it's highly regulated. And in Canada, it's called National Instruments 43101. In Australia, it's called JORC, the JORC code. This is somewhat of a really dry topic, but it's exceedingly important that we understand the language used in these reports. So here is the language sort of structure used in resource assessment reports in the mining and mineral exploration industry. Okay, so your exploration results, there's two columns here, mineral resources, mineral reserves. And as we go down, we have an increasing level of geological knowledge and confidence. And then we have this interchange between resources and reserves defined by what we call modifying factors. Okay, so all that drilling and all those surveys is to amass information from which you can predict the grade and the tonnage of your deposit, the geology. And that's the mineral resources. And you could report an inferred resource, an indicated resource, or a measured resource. And that just depends on how much information you've acquired and what the risk is, the uncertainty of those inputs when you make a model of your deposit. This is all geology. This is just minerals and grade and tonnage and all of that. This is the resource. If we want to talk about reserves, this now becomes an economic question. We're now talking about, okay, we take our information from our geology and we apply our modifying factors. These are all the other factors, except for geology, that decide whether or not you can have a mine there. So there's how are you going to mine it? How are you going to process the ore? How are you going to extract the metals from the minerals? What are the economics? What's the price of gold? What's it going to be in 5 years? There's the marketing, there's all the legalities of opening a mine, there's all the environmental considerations. You're going to have to build roads, you're going to need power, you're going to need water. Social, you're going to disturb local communities, you're going to have to bring in a workforce. Where are you going to train these people? And then government factors, licensing again, things like royalties and taxes. All of that needs to be calculated in order. The question in the end is your mine going to be profitable? That's it. You figure out how much metal is there, and then you figure out how much it'll cost to mine it. And if the value of the metal is worth more than the cost, then you have mineral reserves. Only now, this is a real technicality, can you start talking about ore. So an ore deposit is any deposit where you have a defined mineral reserve. Before that, technically, it's not ore. Ore is something you can extract out of the ground at a profit. So back over here, you might have a mineral deposit, but it's not an ore deposit. Little subtlety there. Okay, so we go back to Saltwater 1. Nautilus Minerals, they never actually defined a reserve. All this time, they got a mining license from the government of Papua New Guinea based solely on their mineral resource in two classes: inferred, which is the less confident, and indicated resource. But they were the first ever company to come up with any sort of resource assessment for the seafloor. What is very interesting, and what I would consider to be huge news, is something that came out of the metals company only a couple months ago. So TMC, the metals company, they are not involved in massive sulfide deposits. They're interested in nodules. But they recently released the first ever nodule reserves and the first ever any sort of reserve, mineral reserve from the seafloor. So this is a giant leap forward in terms of deep sea mining. So TMC releases two economic studies with combined net present value of 23.6 billion US dollars and declares world first nodule reserves. I'm just going to pull out a few of the highlights text from this report. Again, you can see this report online. So this is reported as part of subpart 1300 regulation SK. This is a US-based Securities and Exchange Commission. This is sort of their rule book, similar to Canada's 43101 or Australia's JORC. So combined project value, $23.6 billion, showing potential economic viability. This is why it's a reserve, not a resource, of its NORI-D project and significant scalability across the other NORI and TOML areas. Net present value of NORI-D, $5.5 billion. This is based on their pre-feasibility study. I'll show you what that is in a second. So they have a reserve of 51 million tons of nodules. And then they also have, in addition to that, measured, indicated, and inferred mineral resource of another 274 million tons. These estimates, they don't quite have the same confidence that they do for these over here, so they're classified differently. And then lastly, what people really want to know is, well, how much money are they going to make doing this, assuming they actually can? So here's just showing how much metal they have in their reserves, how much it'll cost to extract those metals. That's not just the mining, that's getting them to market. So that involves refining and processing. So the projected after-tax net present value is 5.5 billion. So that's sort of, you could think of it loosely as the profit after all of that. And after-tax internal rate of return of 27%, which is essentially the ratio of profit to overall expenditure. And it's sort of a measure of the risk of how close are they from being profitable versus not profitable. Okay, let's go back to let's sort of summarize everything we've just gone through from our prospector and his donkey to a reserves. So on this plot from left to right is essentially time. And then on the bottom, we have a lot of the different stages of exploration that we've been going through. And then the red line on a logarithmic scale, which is important, is how much this all costs. So regular land-based mining, you have your prospector, very low cost, conceptual, getting out there, walking around, smashing some rocks with a hammer, and just looking to find any indications of mineralization. You find something, you start to spend some time and money developing it, set up a camp. You might start drilling if you think that you have something there. And then if you're successful and your deposit is large enough and rich enough, you will do feasibility study, which is essentially what the metals company just did, start to factor in all of the economics. And then you make a decision. Is this going to be a mine or not? And if you decide it is going to be a mine, your expenditures go way up because building a mine is incredibly expensive. And then you have a mine. And then eventually the mine has a lifespan, and afterwards it closes and you spend more money on remediation. Okay. On the seafloor, if we plot what Nautilus Minerals basically made it to the pre-feasibility stage. They developed a resource. They did some drilling. They defined an ore body. No, that's not correct. They defined a mineral deposit because they never actually calculated reserves. They never actually had an ore body. And then they ran out of money. The metals company has made it a little bit further. They've defined a reserve, and they're at the point now where they're near decision time with respect to turning this into a mine. We can then add all sorts of complications about, well, the ISA doesn't actually have regulations in place and blah, 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 but the US does. But for now, this is as far as companies have got with respect to the traditional land-based exploration through to exploitation pipeline. This is where we are at the seafloor. Okay, what does this all mean for seafloor massive sulfide deposits? What information do we have where we can assess grade and tonnage and the resource potential of all of these dots on the seafloor? So here's where we can start having some fun with estimates and predictions, because the data available for the seafloor, for massive sulfide deposits especially, is very poor and very sparse, and in most cases, highly uncertain. Okay, back in 2010, 2011, myself with Mark Hannington, Sven Peterson, Thomas Monarchy, and Stace Bildia, we attempted to ask a simple question, which is on the global modern seafloor today, or over a decade ago now, based on the available information at the time, how much massive sulfide is on the seafloor? What is the global resource potential for seafloor massive sulfide deposits? So we published a couple papers on this, one in a Society of Economic Geology special publication, and then a paper in geology. And we use this thing called the three-part resource assessment, which was developed to essentially do these estimates on land. You figure out where on the seafloor can you form these deposits, where is the geology appropriate for that, what are the number of deposits in known well-explored areas that we can then extrapolate, and then grade and tonnage models. And I'll show you what those are. Okay, to estimate the number of deposits, basically we work our way along mid-ocean ridges and arcs and back arcs where we know these deposits are forming, and we go to sites where they are very well explored, and we simply count the number of deposits, and then extrapolate that to the entire global mid-ocean ridge and arc and back arc system. And when we did that, we came up with an estimate of about 1,000 deposits on the seafloor, 1,000 high temperature hydrothermal systems on the seafloor. We then took about 90 deposits for which there was any sort of estimate of the size of those deposits, and we produced a tonnage model. So this is what a tonnage model for SMS deposits looks like. On the x-axis, we have tonnage in a log scale, down 100 tons here, 10 million tons there. On the y-axis, we have cumulative percent. So the way you read this is you could start up here, but 100% of all your deposits on the seafloor are at least 100 tons. And as you work your way down, you get to 50%. That means 50%, half of your deposits, the median value, are at least, in this case, 70,000 tons. So half of the deposits will be larger than 70, the other half will be smaller than 70,000 tons. And your 90th percentile, your top 10%, so 1 out of 10 deposits will be at least 1.6 million tons based on these estimates and fitting a curve to that model. So we now know sort of the size distribution of these deposits. We know how many deposits they're expected to be. And you add up those 1,000 deposits, which will all fit somewhere on this curve. And we got an estimate of, I think our current estimate is 760 million tons of massive sulfide on the seafloor based on this data set we have from Interridge. Now, what does that number mean? 760 million tons. Various estimates suggest that probably any one deposit, for it to be economic, for it to be something we'd consider mining, has to be probably around 2 million tons if you have any chance of making a profit. So 2 million tons means that that's less than 1 in 10 deposits on the seafloor fits that criteria. Overall, 760 million tons. We upset many people when we produce that number because that's an incredibly small number. To give you some perspective, there are copper mines, we call porphyry copper mines, in Chile and Peru, the US, Indonesia, that are billions of tons. Escondida, I think, is the largest porphyry copper deposit in the world. That's a 2 billion ton deposit. That's one mine in Chile. So 760 million tons as the global estimate for the resource potential seafloor massive sulfide deposits is a very, very small number. Okay, what about grade? Like I keep saying, and I will keep saying this over and over again, mining, unlike other things, it's not all about size. It is size and tonnage. You have to have a big deposit and it has to be rich. So in a way, size on its own is useful, but we always have to consider grade. Okay, right. So there's all those numbers. So we produce grade models the same way we produce tonnage models. We took samples and data collected from 95 deposits on the seafloor, ended up being almost 4,000 individual samples, and we looked at the results of analyses for copper, zinc, gold, silver. And again, you get these models. In this case, it's concentration on the x-axis and cumulative percent on the y-axis. And I'll just summarize the median deposit grade. So copper, 4.3%. That's okay, not great, but not bad. Zinc, 10%, that's okay. A little bit of lead, a little bit of gold, and a little bit of silver. These are the median values. The problem with these values, where we have to be very careful, is we have to consider where these values are coming from. And that comes down to how we sample these deposits. So here's a video of us sampling a deposit. This video is sped up 8 times because it takes forever. This is from a Schmidt Ocean Institute cruise in 2016 to Niue volcano. And there we picked up a chunk from a black smoker. You see essentially 2 minerals in there. The shiny stuff is chalcopyrite, which is the main mineral that contains copper. And then the white stuff is some anhydrite. Now, for decades, when we, the community, have been sampling these deposits at the seafloor, this is the majority of the samples that we are collecting. We are collecting samples from active high temperature chimneys because these are the samples that all the different branches of science are mostly interested in. The problem with that is that the high temperature chimneys, the black smokers, the real blingy things we always drive towards, are also the richest parts of the deposits. Higher temperature, the richer the deposit, generally speaking. And so what we've been doing for decades is high grading our sampling of these deposits, resulting in inflated estimates of the concentration of metals in these deposits. What we need to be sampling is the mounds on which the chimneys are sitting. And this is very nicely illustrated if we go back to the table from Nautilus Minerals resource assessment of Solwara 1. And I'm going to focus on this box. So we have our chimneys, our sediment, and our mound. And if you look at the tonnage, if you look at chimneys and sulfide dominant, so the chimneys and the mounds, very little of the material is chimney material. The bulk of your deposit is the mound. But if you look at the grades, copper, higher in the chimneys, 11% versus 8. If you look at gold, 17 grams per ton instead of 6. Silver, 170 instead of 25. Zinc, 6% in the chimneys, average of 0.6%, so 1/10 of that value in the actual mound. And again, the mound is generally your deposit when you think about the relative tonnages of each. IODP drilling at TAG, essentially see the same thing. You compare the drill core metal concentrations to samples collected from the surface of the mound, and you see a similar relationship. So we take that information. This is another typical plot we use in the mineral exploration mining industry. We have deposit size on a log scale on the x-axis and average grade. In this case, we've added up our base metals, total weight percent, again, a logarithmic scale on the y-axis. The data I'm showing you right now is a global database of VMS deposits, volcanogenic massive sulfide deposits. These are essentially SMS deposits that have been preserved in the ancient rock record and have been mined on land for millennia, actually. So all of these deposits are land, your typical land-based mine, underground, open pit, but they all formed on the seafloor in the exact same way that SMS deposits are forming now. So we did this analysis of grade and tonnage of seafloor massive sulfide deposits, and there are 65 deposits for which we have reasonable estimates of grade and tonnage for the same deposit. We plot those on here, and we see that in terms of size, that we're definitely at the low end, especially all these ones down here. But we're at the high end. So low end, sorry, for tonnage, but high end for grade. But I just discussed the issue with grade, and it seems like grade is probably could be up to 10 times in the surface deposits as it is in the actual mounds themselves. So we have to adjust this essentially down an order of magnitude. We could argue for days about how much to adjust this, but for illustrative purposes, we put it down here. Okay, what is this showing us is that seafloor massive sulfide deposits are really not all that interesting in terms of their grade and tonnage compared to what we have preserved in the rock record. You're like, huh, well, that's kind of funny. Uh, that is Solwara 1. So that is, again, Nautilus Minerals, about 2 million tons, and combined base metal, you're at, I think, 8% overall for the deposit. Now, Nautilus Minerals almost mined Solwara 1, but didn't. And you talk to people, and this red line essentially represents the cutoff that we might expect for what you need in terms of combined grade and tonnage to mine the seafloor today. So the higher the tonnage of your deposit, the lower the grade that's required, or the higher the grade, the lower the tonnage. But there's our general relationship. You see that Solwara 1 sits right on the cusp of that line, and everything else for which we have both grade and tonnage data sit below that line. Now, is this a surprise? To someone in the mining industry, probably not. And to illustrate that, we go to Toronto, to PDAC, Prospector Developers Association of Canada, the world's premier mineral exploration and mining convention. This is a huge conference. It's basically the annual mining and mineral exploration conference for the world. Close to 30,000 people attend. Usually about 135 countries are represented. Over 1,000 companies show up. And I highly recommend going to this at least once. It's an amazing conference. You learn a ton. So here's some photographs from what this conference looks like. So there's thousands of companies here, and all of them are pitching a story to investors. They all have a property with a prospect or a deposit that they're developing. Maybe they're just prospecting. Maybe they've been drilling. That whole range, they're there trying to raise money and convince people that they should invest so they can continue to develop that and hopefully turn it into a mine. If your property turns into a mine, you and all your friends become very rich. Now, historically, the proportion of properties that are developed and explored that become mines is somewhere between 0.1 and 1%. So if you look at all of these thousands of companies, between 1 and 10 of them might actually successfully find a property that they turn into a mine. So the chances that you find a mine are extremely low. Most exploration geologists will go through their entire life and never find a mine. That's just the reality. And the reason for that is because ore deposits are geological freaks of nature. They're not normal, they're not regular, they're a perfect storm of geological processes, spatially and temporally combined, that produce geological freaks of nature. So we take that and we go back to our seafloor. And here we have our prospects. We found all these sites of hydrothermal activity. And chances are that 0.1 to 1% of all of these has the potential to become a mine. Now, do our data based on our analysis of grade and tonnage support that? Well, let's take a look. First thing we're going to do is I removed all of the active but unconfirmed dots. So all the blue ones disappear. We have zero information of those sites in terms of grade or tonnage, so they're not very useful for us. So let's just remove those for now. So what's left? We have inactive and active and confirmed. Okay, let's get rid of, wait, what did I get rid of? what's going on here. Okay, right. So yellow and green. Yellow are active. Let's, for sake of argument, assume that there is a wholesale global ban on the mining of active vent sites because of the risk to the ecosystems at these sites. This may or may not occur, but let's pretend it does. So we take all of the active sites off the board. And based on the InterRidge database, there are now 55 sites left on the seafloor. And 1 in 100 or 1 in 1,000 will likely be of economic potential in terms of combined grade and tonnage, which means maybe one of these dots. Well, what do we know based on our estimates of grade and tonnage? There are 3 inactive hydrothermal vent sites on the seafloor that we know of today, for which we have decent grade and tonnage information that would make the cut to be potentially interesting from an economic point of view. So at least 2 million tons and at least 10% combined copper, zinc, lead. There's the Zona field, which is in Indian Ocean, Central Indian Ridge. This site is in the German exploration license. And then there's Semyonov 4 and Krasnov in the Russian exploration license on the Mid-Atlantic Ridge. So 3 sites that are inactive that right now meet that bar of potentially economically viable. Let's say we don't have a ban on mining active sites. So let's put some of the active sites on. We add a few more dots, 1, 2, 3, 4, 5 more dots. Middle Valley, which is probably the biggest deposit by far. I probably should add Red Sea in here, but that's a whole other kettle of fish. Tag, active, but quite big. Over here, here's our Solwara 1 in Manus Basin. And then on the Isibonin Arc, we have Bayonnaise Knoll and Sunrise deposit. This is just based on tonnage. I'm only talking about tonnage right now. These are all big enough. Okay. Now, tonnage and grade. Well, nothing on the Mid-Atlantic Ridge, most mid-ocean ridges are all that interesting in terms of grade. We see that, where did my pointer go? Over here, Middle Valley has disappeared. Zona field still makes the cut, just barely. But it's these deposits over here in the subduction zone related region that stand out, the 2 on the Isibonin and then the Solwara 1 deposit, in which we have grade and tonnage that make these economically interesting. Okay. In terms of reliable data, that which we actually know for sure, again, we only have 1 dot. So Solwara 1 is the only deposit where we actually have enough information that we could reliably state any sort of resource, because it's the only one that's been drilled. To the extent necessary to do these sorts of models. Okay, so takeaway message. The important thing to learn here is that not every hydrothermal vent field on the seafloor is or will ever be a target for mining. And based on what we know now and based on the economics, very, very few, only a handful, have the grade and tonnage that make them economically interesting and even remotely competitive with other sources of metals. And where we're likely going to find most of them will be over in this area. That's a very depressing assessment of seafloor massive sulfide deposits on the seafloor from a resource perspective. It makes me sad because I'm a geologist, and many geologists are driven by exploration and finding the big thing. Every geologist dreams of doing that. And I still hope one day I'll find the big one. But in terms of what the data tell us, right now is that there's very little potential on the seafloor. But I'm not going to end on that negative note. So if we go back to this plot, this is the last thing I'm going to say. Um, we have this region where in the ancient rock record, we are forming these big deposits. Okay, some of them are quite old, Archean, and things were different back then. It's easier to form big deposits. But still, what these data show us is that there is potential on the seafloor that we should be able to find some big deposits. We just haven't found them yet. So where are they? If we go back to our favorite little map here, we're constrained by a number of things. Finding inactive deposits is very difficult because there's no plume. So the potential for more green dots on this map is huge. How huge, I don't know. I don't think anyone knows yet. But there is a lot to be discovered still. We are restricted these days to looking on axis because that's where the activity is. But if we're looking for inactive sites, you can go off axis. Remember that all oceanic crust generally formed at a mid-ocean ridge. So all oceanic crust should host SMS deposits. Now, as you go off axis, they become harder to find because you have sediment. In the future, can we see through the sediment? Could we mine through the sediment? Maybe, but right now, essentially, we're only considering deposits that are exposed at the seafloor. They also oxidize away. So what's the preservation potential of these deposits? Hard to say. They're preserved in the ancient rock record, so we know they're preserved somehow. How does that happen? Where? When does that happen? We don't know. So there's still a lot to be discovered. But again, based on the information we have now, there's very little prospectivity on the seafloor for these deposits. Okay, I am going to stop there, and I'm happy to take any questions that y'all might have.